Hello, I would like to perform a problem which requires understanding of rotational motion and linear motion. In particular, this will be a problem having two-dimensional motion and subject to both centripetal and linear acceleration. That is, radial and tangential acceleration. So, let's go ahead and have a look at this problem. A particle moving in a circle is subjected to a total acceleration that has a magnitude of 8.2 meters per second squared. The radial acceleration has a magnitude of 3.3 meters per second squared. A. What is the magnitude of the tangential acceleration in meters per second squared? B. Find the angle between the acceleration and the tangential acceleration. C. How fast is the particle moving after 5 seconds if it starts from rest? Okay, so first of all, I think in order to get our handle around a problem like this, we should probably draw a picture. So I will introduce the idea of a circle here. Okay, so let me see if I can just sketch a circle here. Okay. So this is meant to be the path that the object is on. Okay, so I'll move this up here. Okay, so again, I'll label this as the path. Okay, so the object's going to move in a circular path. It's subject to a total acceleration of magnitude 8.2 meters per second squared. Let us write this down. Okay, so a total acceleration vector magnitude is 8.2 meters per second squared. We know the radial acceleration is a magnitude of 3.3 meters per second squared. So let's go ahead and write that down, maybe in red, that the radial acceleration is equal to 3.3 meters per second squared. And again, that's a magnitude of this vector. And then, so that's right here. And then we also know we want to know the magnitude of the tangential acceleration, so I'll do that one in blue. Okay. So part A is we want AT vector magnitude. Part B, we want to know the angle between the acceleration and the tangential acceleration. Okay, so that's going to be, let's see here. Part B is we want phi. Let's call this angle phi. Phi is usually a good value to put, or a symbol to put, when you're looking at the relative angle between two vectors, sort of the smallest angle between them. And C, how fast is the particle moving after 5 seconds if it starts from rest? So in part C, we're given that the initial speed is 0 meters per second. So that's the initial speed, magnitude. But it says how fast is it moving? So that's v vector at t equals 5 seconds. We want to know that magnitude, its speed, if it starts from rest. Okay, so let's go ahead and start to draw a bit more of the picture here. Okay, so imagine that the particle is going, let's have it go counterclockwise. Now, by the way, counterclockwise is when it comes to angular rates of rotation, it's going to be positive. But let's go ahead and examine the particle, let's say, right here. Well, yeah, that's fine. And then let's also assume it maybe starts right here. So let's assume this is the start at t equals to 0 seconds. And suppose we're analyzing this particle. So radial acceleration is always directed inward toward the center of the circle. Okay. And note that it's somewhat small. because it's 3.3 meters per second squared. And we want to know the tangential acceleration. So first of all, let me sketch the radial acceleration, which again is somewhat small and towards the center of this circle. Whoops. Okay, good enough. Okay, so this is meant to be a sub r, the radial acceleration. Okay. Now, by the way, we know this particle starts from rest, so it has to have a positive tangential acceleration, which is bringing it in the direction it's already going. By the way, let's label this to be the center of the circle, somewhere about right there. Okay. And then furthermore, let's get the tangential acceleration. Now, because the total acceleration is 8.2 meters per second squared, I'm believing the tangential acceleration is probably a little bit larger. But it should also be tangent to the path that the object is moving, and it should be somewhat, like I said, somewhat larger. Okay? So something like this. Okay? So this is AT, the tangential acceleration. Okay? Remember, this causes the object to move in circular motion, a sub r. A sub t causes the object to speed up. Now, by the way, I think that part A, now by the way, one more thing I should say. Notice that the sum of these two vectors is going to give us this right here, which is a total. So the total acceleration is the vector sum of AT and AR. In fact, let me kind of break this out so that we can see this a little better. Okay, so let's see. Somewhere over here, we have something like this is a total. Okay, so this is a total. It's a vector. We have AT and AR. Now, I'm going to draw it in a very specific way so that we can really analyze. So AR is something like this. AR vector. And then we also know AT. Hopefully you're getting the notion that when we add these vectors together, I think they form a right triangle. Okay? Where this is phi, and then we know that the hypotenuse is given by a total, and then AR is the sort of opposite leg from phi, and then AT, the tangential component, is sort of the adjacent leg to this phi. AT. Okay? Now again, I'm going to say that's probably not necessarily obvious as you work through this problem, because again, we're looking for this tangential acceleration. That's not necessarily obvious until you really sort of sketch it out. So sometimes doing these sketches is really helpful. Okay. By the way, these sketches here are just meant to be, this is the particle at some point of interest. Okay. So that's the idea. All right. So let's see if we can answer part A. So part A, we want the tangential acceleration. So I hope that you can see that if A total is the hypotenuse, at least in terms of its vector magnitude, and AR and AT are the vector legs, we should be able to solve for AT. So we can say A total squared is equal to, and it should be the radial component squared plus the tangential component squared, because this is the Pythagorean theorem in 2 dimensions. So as long as we're working 2-dimensionally, we assume the path is in the plane. This is what we have. Okay, so I think we can solve this for AT, the tangential acceleration, by subtracting the radial acceleration and going ahead and taking the square root. Let me actually look to make this look a little nicer too. These squareds are on these terms. Okay, so let's go ahead and subtract the radial acceleration squared and take the square root. By the way, when we take the square root, we're just going to take the positive square root because we're just looking at magnitudes here. So it should be a total squared minus AR squared, and the square root should equal to AT. And hopefully you appreciate the use of color, okay, because that's just giving you a notion of how these vector accelerations are related together. Okay, so let's put in the numbers because we should be able to get this tangential acceleration. All right. In fact, I want to move this over just a bit so I have a little more room so I can fit this in. Fine. Okay, so this is the square root of, let's see here, the total acceleration was 8.2 meters per second squared. So this is going to be 8.2 meters per second squared. And we have to square that and subtract the radial acceleration, which was 3.3. So, whoops. So, minus 3.3 meters per second squared. And we have to square that as well. Okay, so now the calculation. So, let's go ahead and type in second square root 8.2 squared minus 3.3 squared. Okay, so that should be about 7.51 rounded to 3 significant digits or so. Okay, and we can probably just leave it as 7.5 because I think that we were only given 2 significant digits. Okay, so let us write this down. So this is AT is approximately 7.5 meters per second squared. Okay. Indeed, like I predicted, it is quite a bit larger than the centripetal acceleration. So this object is speeding up quite a bit as it goes along, but its centripetal acceleration is always staying like the same, or at least like, yeah. I mean that's the acceleration it's retaining. Okay. So let's assume both of these, all these values, by the way, are constant. Okay, let's see. B, find the angle between the acceleration and the tangential acceleration. So I think that's phi, okay? So I think for phi, we can probably use the following. We can probably say, okay, even if we made a mistake on AT, we know what AR and A total are. So I think that opposite over hypotenuse is the sine function. So the sine of phi should be, let's see, AR divided by A total. Okay, so this is AR divided by A total. So let's put the numbers in. So AR, oh, and by the way, we should perform inverse sine, so I'll do that on the next line. So we'll just say the inverse sine, or the arc sine, of AR over A total gives phi. So then AR being 3.3 meters per second squared, okay, and we're going to say phi is equal to the inverse sine of this number over this other number, A total, which was, let's see, it's 8.2 meters per second squared. Okay, let's return to the calculator. Now, for this problem, we certainly have to make sure our calculator is in degree mode because we're looking for things in degrees. So this shows to be in degrees. So I clicked on mode, and then I'm going to scroll down to where it's radians, go over to degrees, hit enter. Okay, so I'm going to second quit out of this, and I'm going to, let's just clear, and let's do second sine, which is inverse sine, of 3.3 divided by 8.2, and this should give us an angle in degrees. So let's write this down, 23, about 24 degrees, again, to 2 significant digits. Okay, so this is approximately 24 4 degrees. All right, fine. So that takes care of part B. Okay. And finally, part C. So part C says, how fast is the particle moving after 5 seconds if it starts from rest? Well, the idea is that the speed will only be determined by the tangential acceleration. So I think we can use linear kinematics, that is one-dimensional kinematics, for constant acceleration if we know the time, okay? And by the way, with the linear kinematics, I think we want to think about which kinematic equation. So we can use 1D linear kinematics for constant acceleration using the tangential acceleration. Okay. And furthermore, we know that the equation that we should choose in terms of kinematics is the one that ignores the kinematic variable that we're not interested in. Now, I think the variable that we're not interested in is delta x. Now, delta x would actually be a curved distance all the way around. It's more like a delta s, but that'd be sort of the total sort of linear distance all the way around. So we're not really interested in how far it goes. We're interested in its final velocity when we have the initial velocity and we also have the acceleration and the time. So I think that that suggests, so this suggests the definition of acceleration equation. Okay, so let's go ahead and see if we can write that down. Okay, so I think that the final velocity should equal to the initial velocity plus the acceleration times the time. And the acceleration again here is the, I'm just changing to blue for emphasis, the tangential acceleration. Okay, so let's put those values in. Okay, so again, this tangential acceleration is going to be what we just found before, which was 7.5 meters per second squared. I just want to write that in first because I have the blue color out and the rest will be in black. So let's see. That is multiplied by a time of 5 seconds. And we have to add to that, well, the initial velocity is 0. Okay, so we don't even need to worry about this initial velocity. I could have just written a 0 right there. But let's go ahead and just multiply 7.5 times 5 seconds to get this final velocity. So, calculator. So, calculator. We just need 7.5 times 5. Okay, so 37.5 meters per second. Okay, and this would be our final answer for the magnitude of the final linear velocity. Remember, even though this thing is moving in a circular path, you could imagine that its velocity anywhere on the outside is given by a linear or a tangential velocity. That is, at any moment, I mean, you could imagine that if the velocity here were, say, in green, that, let's see, so if this is the velocity, and this is a velocity, you could imagine at the start v equals 0, but then as we go along, the tangential velocity gets faster and faster because we're tangentially accelerating. So you could imagine maybe at some point, say over here, after it's made, say, maybe more than one full revolution, or just about one full revolution, let's say, its tangential velocity is even larger. Okay, so that's kind of what this 37.5 meters per second represents. These are vectors of the velocity. Okay, thank you very much for your attention, and thank you for understanding this two-dimensional motion problem. If you like this content, please smash that like button, And please subscribe to the channel to grow the channel. Please share this with people within your sphere of influence, especially if it can help them. Thank you for watching High Peak Education, and I will see you in the next video.